Welcome to our deep dive. You ready to jump into some statistics today?
Always.
I knew you were going to say that. You've shared some excerpts from a business statistics textbook.
Right.
So we're going to dissect those and see what we can uncover. I'm guessing you're either gearing up for a class, brushing up on some fundamentals, or perhaps you just find data fascinating.
Oh, yeah.
Whatever your reason, we're here to
Absolutely.
help you extract those golden nuggets of knowledge from these excerpts.
It's a great subject. What's so fascinating about statistics is that it goes beyond just crunching numbers.
Right.
It's a way of thinking, a lens for understanding the patterns and trends that shape our world.
I like that. So if statistics is about making sense of the world, where do we even begin? The text mentions two main branches,
Yeah.
descriptive and inferential statistics. Are those the foundational pillars?
Absolutely. Descriptive statistics is all about summarizing and presenting data in a way that's easy to grasp.
Okay.
Think charts, graphs, and calculating those familiar averages. It helps us to paint a picture of what our data looks like.
Okay, so descriptive statistics helps us organize the raw data. But what about going beyond just description? What about using data to draw conclusions and make predictions?
That's where inferential statistics comes in.
Okay.
It's like detective work, really.
Yeah.
Using data from a sample to make educated guesses about a larger population.
Right.
For example, imagine trying to predict the outcome of an election.
Okay.
It's impossible to ask every single voter, right?
That would be a logistical nightmare.
Exactly. So instead, we carefully select a sample of voters,
Right.
and we use their responses to infer what the large voting population might think.
Okay.
This is the power of inferential statistics.
I see. And I remember the text mentioned probability playing a big role here. Something about tossing a coin.
Yes. The coin toss is a classic example.
Okay.
While the outcome of a single toss is uncertain, probability allows us to predict the long-term pattern. The more you toss the coin, the closer the results will get to a 50-50 split between heads and tails.
That's interesting. So we're using these patterns in randomness to make more informed predictions about things that seem uncertain on the surface?
Precisely. And that's a fundamental idea in statistics.
Okay.
Now, before we get too deep into the inferential side of things, let's make sure we're clear on some basic terminology.
Good point. The text does use a lot of terms
Yeah.
that might be new to someone just starting out.
Right.
With statistics, let's tackle those head on.
Okay.
We often hear about populations and samples, but what do those really mean in a statistical context?
Think of it like this.
Okay.
A population is the entire group you're interested in studying.
Right.
It could be all the students at a university,
Right.
all the trees in a forest,
Yeah.
or even all the stars in a galaxy.
Okay.
But in most cases,
Yeah.
it's impossible to gather data on every single member of a population. It would be incredibly time-consuming and expensive.
That makes sense. So that's where sampling comes in, right?
Exactly. A sample is a smaller, more manageable group
Right.
selected from the population. The key is to ensure that the sample accurately represents
Right.
the population we're interested in.
So a good sample is like a miniature version of the population.
Yeah.
Like a well-chosen spoonful from a big pot of soup, giving you a good idea of the overall flavor.
That's a great analogy.
Okay, good.
And once we have our sample, we collect data on specific characteristics,
Okay.
which the text refers to as variables.
Right.
These variables can be anything we can measure or observe, like height, age, income,
Okay.
or even opinion on a certain topic.
So if we were studying the reading habits of college students, number of books read per month could be one variable.
Sure.
And preferred genre could be another.
Exactly. And then there's data, which are the actual values we collect for these variables. So if we ask a student how many books they read last month and they say 3.
Right.
That 3 is a data point.
Okay, I'm starting to see how these pieces fit together.
Yeah.
But the text also mentions something called parameters and statistics.
Yeah.
Are those related to populations and samples?
You're right on track.
Okay.
A parameter is a numerical characteristic of a population. For instance, the average height of all students at a university would be a parameter.
Okay.
But since it's usually impossible to measure everyone in the population, we use statistics to estimate parameters.
So a statistic is like a stand-in for a parameter.
Exactly. It's a numerical characteristic calculated from a sample. So if we take a sample of 100 students and calculate their average height, that average would be a statistic, and we could use it to estimate the average height of all students at the university.
This is making a lot more sense now.
Good.
We use statistics from a sample to give us a glimpse into the parameters of a whole population. It's like using a flashlight to explore a vast, dark cave.
I like that. And understanding the difference between parameters and statistics is key to grasping the power of inferential statistics.
Now, the text also dives into different types of data. It mentions qualitative and quantitative data. Are those the main categories we need to know?
Those are the two primary types, yes. Qualitative data describes qualities or characteristics.
Okay.
Things that can't be easily measured with numbers.
Right.
Think colors, brands of cars, or types of music.
Okay, so qualitative data is about categories and descriptions. What about data that can be measured numerically?
That's our quantitative data. This type is all about numbers and measurements.
Okay.
Things like height, weight, temperature, or exam scores.
So if we're measuring how many hours students study per week, that would be quantitative data.
Exactly. And within quantitative data, we have another layer, discrete and continuous data. Discrete data is countable, like the number of children in a family or the number of cars in a parking lot. You can't have half a child or half a car, right?
Right. Those have to be whole numbers.
Yep.
So what about data that can take on any value within a range?
That's our continuous data. Think things like height, weight, or time. You could have a height of 5'9",
right,
or 5'9.5", or even 5'9.55". You can keep getting more and more precise.
I see. So understanding the type of data we have is important for choosing the right statistical tools and techniques. It's like selecting the right wrench for a specific bolt.
Exactly. The type of data dictates how we analyze it, and what kind of conclusions we can draw.
All this talk about data is making me realize how important it is to collect it properly. The text emphasizes the importance of sampling.
Yes.
Is that the key to gathering reliable data?
Absolutely. The way we select our sample can make or break our study. If our sample isn't representative of the population, our results might be misleading.
So we can't just choose any random group of people or things.
Not if we want our findings to be accurate and generalizable.
Right.
The text highlights random sampling as a crucial method for minimizing bias. Imagine you're trying to understand the music preferences of all students at a university. You can't just survey your friends, right?
Right. That would be a very limited perspective. What would be a better approach?
A better approach would be to use a technique like simple random sampling, where every student has an equal chance of being selected for the survey. This helps ensure that our sample is a more accurate reflection of the entire student body.
So random sampling is like shuffling a deck of cards before dealing a hand. It ensures that everyone has a fair chance of being represented.
Exactly. And this is crucial for minimizing bias. And making sure that our statistical insights are reliable.
This is fascinating. I'm starting to see how much thought and strategy goes into collecting and understanding data. It's not just about crunching numbers. It's about choosing the right methods and techniques.
Absolutely.
To ensure that our insights are meaningful and accurate.
Absolutely. And that's what makes statistics such a powerful tool for understanding the world around us.
Now, even with the best sampling techniques, we're bound to have some variation in our data, right?
That's right.
No two samples from the same population will be exactly alike.
We're dealing with the inherent variability of the world. Imagine two researchers, both studying the average sleep duration of students at a university. They both use random sampling, but they end up with slightly different results.
So how do we make sense of this variation? How do we know how much variation is normal and how much is meaningful?
That's where data visualization comes in. Creating visual representations of our data, like those charts and graphs we talked about earlier, helps us see patterns and understand the shape of our data. Before we even start doing any complex calculations.
So data visualization is like creating a map.
Exactly.
Of our data landscape.
It helps us see the big picture and identify any interesting features or trends. The text mentions several visualization tools, each with its own strengths. For instance, a stem and leaf plot is great for showing the distribution of individual data points. It's like taking a closer look at the individual trees in our forest.
And what about those bar graphs we see everywhere?
Bar graphs are excellent for comparing categories, like the sales figures of different products or the popularity of different music genres. They give us a quick and easy way to see the relative sizes of different groups.
So we've visualized our data and we're starting to see some patterns. So what happens next? Do we start calculating those measures of center and spread the text mentions.
You got it. Those measures are like the building blocks for summarizing and describing our data numerically.
Okay.
They help us answer questions like, what's the typical value in our data set?
Okay.
How much do the values vary?
I remember the text talking about the mean, median, and mode
Yeah.
as measures of center.
Mm-hmm.
Could you refresh my memory on those?
Of course, the mean is the one we're most familiar with.
Right.
It's simply the average.
Okay.
We add up all the values in our data set and divide by the total number of values.
But the mean can be sensitive to extreme values, right?
Right.
Those outliers that can skew the overall picture.
The mean can be pulled in one direction or another.
Right.
By extreme values.
Okay.
That's what the median comes in handy.
Okay.
It's the middle value when the data is ordered from least to greatest.
Mm-hmm.
Think of it like a dividing line.
Okay.
Half the values fall above the median.
Right.
And half fall below.
So the median is like a more robust measure of center?
Exactly.
Less swayed by those outliers.
And then we have the mode, which is simply the most frequent value in our data set. It's particularly useful for categorical data, like finding the most popular color of car
right.
in a parking lot.
So depending on the type of data and the question we're asking, we choose the most appropriate measure of center to get a clear picture of the typical value in our data set.
You've got it. Now let's talk about spread, which tells us how much the data varies or deviates from that typical value.
The text mentioned range, standard deviation, and interquartile range.
Yes.
As measures of spread.
The range is the simplest measure.
Okay.
It's just the difference between the highest and lowest values in our data set.
Okay.
It gives us a quick snapshot of the spread.
Right.
But it can be influenced by outliers.
Right, the outliers always causing trouble. What about standard deviation? That one always seemed a bit more complex.
The standard deviation tells us, on average, how much the data points deviate from the mean. Think of it like measuring the average distance of all the trees in our forest from the center of the forest.
So a small standard deviation would mean the trees are clustered closer together, and a large standard deviation would mean they're more spread out.
Exactly. And finally, we have the interquartile range, or IQR.
Right.
This one focuses on the middle 50% of the data, giving us a sense of the spread within that central chunk.
So the IQR is like focusing on the heart of the forest, ignoring those outliers.
That's a great way to put it.
Okay, good.
And just like with measures of center, choosing the right measure of spread depends on the type of data we have and what we want to understand about it.
All this talk about center and spread is making me realize how much we can learn about data just by looking at these basic descriptive measures. It's like getting a feel for the personality of our data set.
Absolutely. And these measures are the foundation for more advanced statistical techniques. They provide the building blocks for understanding patterns, making comparisons, and drawing meaningful conclusions from our data.
And the text also mentions percentiles.
Yes.
Are those related to measures of center and spread?
Percentiles are a slightly different concept, but they also help us understand where a particular data point stands in relation to the entire data set. Imagine you scored in the 80th percentile on an exam. That means you scored better than 80% of the people who took the same exam.
So percentiles are like a ranking system showing us the relative standing of a particular value.
Exactly. And they're used all the time, from standardized test scores to growth charts for children.
We've covered a lot of ground here.
You have.
We've talked about the core ideas behind statistics, the different types of data we might encounter, the crucial role of sampling.
Absolutely.
And the importance of visualizing and summarizing our data.
We've laid a solid foundation. And now we're ready to delve into the more analytical side of statistics.
This is getting me excited to explore the world of inferential statistics.
Me too.
And all the insights it can offer.
And that's where we'll pick up in our next deep dive session. Picking up where we left off, are you ready to dive into the world of inferential statistics?
Absolutely. I'm eager to see how we can use those foundational concepts we discussed to unlock deeper insights from data. The text mentioned probability distributions. Can we start there?
Probability distributions are a fantastic next step. They help us understand the likelihood of different outcomes in random events. Imagine them as a map of possibilities showing us not just what can happen, but how likely each outcome is.
That sounds intriguing, but can you give me a concrete example? My brain works best with visuals.
Let's say you're a quality control manager at a factory producing light bulbs.
Okay.
You're interested in how long these bulbs last. A probability distribution could help you visualize the lifespan of your bulbs. It would show you the probability of a bulb lasting 500 hours, 1,000 hours, or any other duration.
So it wouldn't just tell me the average lifespan, but the entire range of possibilities and how likely each one is.
Exactly, and that's much more powerful for making decisions.
Right.
For instance, if you see a high probability of bulbs failing before a certain time, you might adjust your manufacturing process.
That makes a lot of sense. The text mentioned different types of probability distributions. Is that because different scenarios call for different tools?
You're absolutely right. There is several types, each with its own unique characteristics and applications. One you might find particularly useful is the binomial distribution.
Okay, tell me more about that one.
Think of any scenario where you have a fixed number of trials, and each trial has only two possible outcomes, success or failure. It could be flipping a coin 10 times, where each flip is a trial, or sending out a marketing email to 100 people, where each email is a trial and a success is someone clicking on the link.
So in our light bulb example, a trial could be testing a single bulb, and success could be it lasting longer than a certain number of hours.
Exactly. The binomial distribution would tell you the probability of getting a specific number of successful bulbs in a batch. This could be invaluable for quality control.
That's incredibly practical. What about situations where we're not interested in the number of successes, but rather in how long it takes to get a success?
Great question. That's where the geometric distribution comes in. Imagine you're playing a game where you roll a die until you get a 6. The geometric distribution would tell you the probability of getting your first 6 on the first roll, the second roll, the third roll, and so on.
So for our light bulbs, we could use the geometric distribution to analyze the probability of finding the first defective bulb after inspecting a certain number of bulbs.
Precisely. It's all about that time to first success concept.
The textbook also mentioned the Poisson distribution. Does that deal with successes and failures too?
The Poisson distribution is a bit different. It's great for modeling rare events that occur over a specific interval like time or space. Think of the number of accidents at an intersection in a week, or the number of typos in a page of text. These events happen randomly, but the Poisson distribution helps us estimate their likelihood.
So if our light bulb factory wanted to track the number of defects per production run, the Poisson distribution could be a useful tool.
Exactly. It would provide a framework for understanding the probability of different defect rates and making informed decisions about quality control measures.
This is all starting to click. Now, all the distributions we've talked about so far seem to deal with countable events. What about data that can take on any value, like the height of a tree or the weight of a light bulb?
Excellent point. Those situations call for continuous probability distributions. One of the most famous is the normal distribution, often depicted as that bell-shaped curve you see everywhere.
Oh yes, the bell curve. It seems to pop up in so many different contexts.
It does, and that's because many natural phenomena, from heights and weights to exam scores and blood pressure readings, tend to follow this bell-shaped pattern. Most values cluster around the average, with fewer and fewer values as you move further away in either direction.
So is the normal distribution's popularity due to its prevalence in the natural world?
That's definitely a big part of it, but the normal distribution is also incredibly valuable because of its predictable properties. We know that a certain percentage of data will always fall within specific distances from the mean. This allows us to make probability calculations and predictions with a high degree of confidence.
That predictability sounds incredibly useful for making decisions.
Absolutely. Now, what's interesting is that even though the normal distribution is continuous, it can sometimes be used to approximate discrete distributions like the binomial distribution.
Wait, how is that possible? I thought those were two distinct categories.
It's a clever statistical trick. When the number of trials in a binomial scenario is large, the shape of the binomial distribution starts to resemble that familiar bell curve. This allows us to use the properties of the normal distribution to make estimations, simplifying our calculations.
It's like using a shortcut, leveraging the power of the normal distribution to tackle those more complex binomial scenarios.
Exactly. It's a testament to the versatility and power of the normal distribution in statistics.
Okay, I think I'm starting to grasp the world of probability distributions, but how do they actually connect to the idea of inferential statistics using a sample to understand a population?
That's a great question, and it leads us to a crucial concept: sampling distributions. Imagine you took multiple samples from the same population and calculated the mean of each sample.
Wouldn't we get slightly different means for each sample, even though they're all drawn from the same population?
Exactly, and the sampling distribution shows us how those sample means are distributed. It's like a meta-distribution, a distribution of statistics rather than individual data points.
So the sampling distribution helps us understand how much those sample means are likely to vary from each other.
Precisely. It gives us a sense of the variability we can expect when using a sample to estimate a population parameter.
Okay, I'm following so far. Now, the textbook mentions a particularly important theorem related to sampling distributions, the central limit theorem. Can you break that down for me?
The central limit theorem is one of the most powerful concepts in statistics. It states that as we take larger and larger samples from any population, even if the population itself doesn't follow a normal distribution, the distribution of the sample means will approach a normal distribution.
Wait, so even if our original data is skewed or has a weird shape, the sampling distribution of the means will eventually become normal if our samples are large enough.
You got it. It's a bit like magic, right? The central limit theorem provides a theoretical foundation for many statistical techniques, allowing us to make inferences about populations even when we don't know the exact shape of the population distribution.
That's incredible. So even if we're dealing with messy real-world data, the central limit theorem gives us a way to make reliable inferences.
Exactly. And it's all thanks to the power of sampling and the predictable behavior of sample means as our sample size increases.
This is opening up a whole new level of understanding for me. So how do we actually use these sampling distributions and the central limit theorem to draw conclusions about populations?
That's a fantastic question, and it leads us into the realm of confidence intervals and hypothesis testing, two essential tools in the world of inferential statistics.
Okay, let's dive into those. Starting with confidence intervals, what are they all about?
Confidence intervals are all about estimating a population parameter with a certain level of confidence. Remember, in most cases, we can't measure everyone in the population, so we use a sample to calculate a statistic like the mean, and then we create a confidence interval around that statistic.
So instead of getting a single point estimate like the sample mean, we get a range of values.
Exactly. And that range captures the uncertainty inherent in sampling. It tells us that we're reasonably confident that the true population parameter falls somewhere within that range.
Okay, but how do we determine that level of confidence? What does it actually mean?
Imagine you repeated your study 100 times, each time taking a new sample and calculating a confidence interval. If you have a 95% confidence interval, you would expect 95 out of those 100 intervals to contain the true population parameter.
So it's about the long-run success rate of our estimation method, not the probability that the true value is within our specific interval.
Precisely. It's about the reliability of the process. Now, the way we calculate that confidence interval depends on whether we know the population standard deviation.
And in most real-world situations, we don't, right?
That's right. And when we don't know the population standard deviation, we use a different distribution, the student's t-distribution, to construct our confidence intervals. It's similar to the normal distribution, but accounts for the extra uncertainty introduced by estimating the standard deviation from our sample.
So it's like a more robust version of the normal distribution, tailored for those situations where we're working with incomplete information.
You've got it. The t-distribution is a valuable tool for making inferences when we don't have the full picture.
This is all making a lot more sense now. So confidence intervals provide a way to estimate population parameters with a certain level of certainty. What about hypothesis testing? How does that fit into the world of inferential statistics?
Hypothesis testing is all about putting our beliefs or assumptions to the test using data. It's like setting up a statistical courtroom where we present evidence and see if it's strong enough to convict or acquit our hypothesis.
So it's like having two instruments playing the same note in our orchestra. It muddles the sound and makes it hard to distinguish the individual contributions.
That's a perfect analogy, and we can use various diagnostic tools to detect and address multicollinearity, ensuring that our regression model remains reliable and interpretable.
Okay, multiple regression seems like a powerful tool for unraveling those more complex relationships where multiple factors are at play. Are there any other extensions of linear regression that we should be aware of?
There are a few other specialized techniques that build upon the foundation of linear regression.
Okay.
For instance, polynomial regression allows us to model curved relationships rather than just straight lines,
Okay.
providing more flexibility when dealing with nonlinear patterns in our data.
So if the relationship between our variables looks more like a parabola than a straight line, polynomial regression might be a better fit.
Exactly. It allows us to capture those more nuanced curves and bends in the data.
Okay.
And then there's logistic regression,
Right.
which is used when our dependent variable is binary,
Okay.
meaning it has only two possible outcomes, like yes or no, success or failure.
So if we're trying to predict whether a customer will click on an ad based on their browsing history or demographics, we might use logistic regression.
That's a great example. Logistic regression is widely used in marketing, healthcare, and other fields where predicting binary outcomes is essential.
It's amazing how versatile regression analysis is. It seems like there's a regression technique for almost every type of data and research question.
And that's what makes it such a valuable tool in the statistician's arsenal. It allows us to explore relationships,
Right.
make predictions, and gain a deeper understanding of how variables interact.
This deep dive has been an incredible journey through the world of correlation and regression.
It has.
But before we wrap up,
Yeah.
I think it's important to address a common misconception
Mm-hmm.
that often arises when discussing these concepts, the idea that correlation implies causation.
You're absolutely right. It's crucial to remember that just because two variables are correlated,
Right.
it doesn't necessarily mean that one causes the other. Correlation simply tells us that the variables move together.
Okay.
But there could be other underlying factors, often unobserved,
Yeah.
that are driving that association.
So if we find a positive correlation between ice cream sales and crime rates, it doesn't mean that eating ice cream causes people to commit crimes.
Exactly. There's likely a lurking variable,
Right.
like hot weather, that's influencing both ice cream sales and crime rates.
Okay.
People tend to buy more ice cream on hot days, and crime rates also tend to be higher in warmer weather.
So how do we go beyond correlation and actually establish causation?
Establishing causation requires a more rigorous approach, typically involving carefully designed experiments,
Okay.
where we manipulate one variable and observe its effect on another,
Right.
while controlling for other potential confounding factors.
So correlation can be a clue, a starting point for investigation,
Yeah,
but it's not the whole story.
precisely. It's an important piece of the puzzle, but we need to be cautious in our interpretations
Right.
and avoid jumping to conclusions about cause and effect based solely on correlation.
This has been an incredible deep dive into the world of statistics. We've covered so much ground,
We have
from basic definitions and data types to probability, sampling distributions, confidence intervals,
Yeah.
hypothesis testing, and even the fascinating realms of correlation and regression.
It's been a whirlwind tour
It has.
of some of the most powerful concepts and tools in statistics, and I hope you're feeling more confident and equipped to navigate the world of data.
I definitely am. Like, we've lifted the curtain on a whole new way of seeing and understanding the world. And what's even more exciting is that we've only scratched the surface. There's so much more to explore and discover in the ever-evolving field of statistics.
That's the beauty of it. Statistics is a lifelong journey of learning and discovery,
Yeah.
and the insights it offers are becoming increasingly valuable in our data-driven world.
On that note, I think it's time to wrap up this deep dive. But before we do, I want to thank you for sharing your expertise and guiding us through this statistical landscape.
It's been my pleasure. And remember, statistics is not just about formulas and calculations. It's about a way of thinking, a framework for making sense of the world around us.
So to our listener, keep asking questions, stay curious, and embrace the power of statistics.
And until next time, happy analyzing.